In the tremendous universe where secrets proliferate and the actual texture of spacetime is extended as far as possible, a significant secret has arisen. How we might interpret the development of the universe is at a junction, with new proof testing well-established hypotheses and alluding to stowed-away forces that could reshape the actual groundworks of cosmology. Go along with us on an excursion through the most recent revelations and profound dives into the mysteries of the universe as we investigate the entrancing and disputable question: how fast is the universe truly growing? Something is off with how we might interpret the universe. Cosmology is by all accounts making a beeline for a showdown over perhaps its most central question. How fast is the universe expanding? For over 10 years, two sets of measures have been in struggle. Perceptions of the universe today generally show that the pace of expansion, known as the Hubble constant, is around 9% quicker than expectations based on data from the early universe. Specialists trust the James Webb Space Telescope, the most advanced telescope ever constructed, would assist with settling the question unequivocally. Yet, up to this point, no agreement has been arrived at. Rather, the Space Observatory has built up the disparity with amazingly exact groundbreaking perceptions that took steps to topple the standard model of cosmology. The new physics expected to reconsider or even supplant this 40-year-old hypothesis is now the subject of discussion. One fascinating and charming chance is that there is something we don't comprehend about the universe. Go along with us as we investigate the new, truly profound pictures from James Webb that have recently confirmed that there is something genuinely amiss with how we might interpret the universe. Our universe began with a blast, the Big Bang. Energy, mass, and space appeared in a passing second. Then, the youthful universe formed a gurgling, growing plasma of matter and antimatter particles that seemed to destroy each other on contact. Left to their own devices, the matter and antimatter inside this plasma ought to have drunk one another. Yet, scientists believe that an obscure lopsidedness permitted more matter than antimatter to be made, consequently saving the plasma universe from immediate implosion. Gravity pressed pockets of plasma, compacting and warming the material so that sound waves, traveling at around half the speed of light, called bionic acoustic oscillations, undulated across their surfaces. In the meantime, the high energy density of the early universe and its complicated objects expanded spacetime, pulling a little piece of that matter out of the conflict as the universe swelled like an inflatable. The standard story goes that common matter, interacting with light, combined around undetectable bunches of dark matter to shape the first worlds, connected together by a huge cosmic web. At first, as the objects in the universe expanded, its energy density and hence its pace of expansion diminished. However, around 5 billion years ago, the universe began to accelerate at a continually increasing rate. The reason was a new, invisible, and baffling element called dark energy. The simplest and most well-known explanation of dark energy is that a cosmological constant, an inflationary energy, is the same everywhere and always woven into the fabric of spacetime. Einstein named it lambda in his general theory of relativity. As our universe has expanded, its general matter density has diminished, while the dark energy density has remained the same, continually making dark energy the largest contributor to its overall expansion. Taken together, the energy densities of ordinary matter, dark energy, and light energy set an upper limit on the pace of the universe's expansion. They are also key components in the cosmological lambda-cold dark matter, lambda CDM model, which guides the universe's development and predicts its end, with matter ultimately expanding up to the point that it will experience a phase known as the Big Freeze. A number of the model's predictions have proven surprisingly accurate. However, this is where the problems begin. Despite much research, astronomers still don't know what dark matter or dark energy is. As Ofer Lahav, professor of cosmology at University College London, who studies dark energy in galaxies, puts it, the vast majority agree that the current structure of the universe is 5% ordinary bionic matter, 25% cold dark matter, and 70% dark energy. The embarrassing truth is that we don't understand the latter. A much greater threat to the lambda CDM model has arisen. Depending on the method astrophysicists use, the universe appears to be expanding at different rates, a discrepancy known as the Hubble tension. Trials of the early universe show that it was expanding much faster than lambda CDM anticipated. These methods have been checked and confirmed by numerous observations. As astrophysicist Adam Rees, Nobel laureate and head of the team that made James Webb's new measurement, said, "The only explanation I can understand right now for why they differ is that the model we have between them may be missing something. Measuring the expansion of the universe requires more than just radar." The primary method to measure this expansion looked at the so-called cosmic microwave background, CMB, a remnant of the first light known to mankind, made just 380,000 years after the Big Bang. This remnant is visible all around the sky, and it was mapped by the European Space Agency's Planck satellite to find the Hubble constant with an error of under 1%. From 2009 to 2013, in the Planck image, the universe is completely homogeneous, but the hotter and colder regions, where matter is more or less dense, reveal spots where the bionic acoustic vibrations have caused it to cluster together as the universe expanded outward. This sponge structure evolved into a cosmic web, an intricate network of filaments along the intersections of galaxies. By studying these waves with the Planck satellite, cosmologists have concluded the amounts of ordinary and dark matter, as well as the value of the cosmological constant or dark energy. Incorporating these into the standard model gives a Hubble constant of around 67 kilometers per second per megaparsec. Let's focus on that number for a moment. If a galaxy is 1 megaparsec away from us, that means it is receding from us, and we from it at a speed of 67 kilometers per second. At 20 megaparsecs, this rate of recession reaches 1,340 kilometers per second and continues to increase dramatically. If a galaxy is more than 4,175 megaparsecs away, it is receding from us faster than the speed of light. A second method for finding this expansion rate uses pulsating stars called Cepheid variables, dying stars whose outer layers of helium expand and contract as they absorb and emit radiation, making them periodically blink like distant beacons. In 1912, astronomer Henrietta Swan Leavitt discovered that the brighter a Cepheid star, the slower it blinks, allowing astronomers to gauge a star's absolute brightness and thus estimate its distance. It was a landmark discovery that made Cepheid variables the ubiquitous standard candles for measuring the immense scale of the universe. By combining findings from observations of Cepheid variables, astronomers can build measurements of vast distances, with each step taking them further back in time. It is perhaps the most reliable method astronomers use today to measure distances and build a cosmic distance ladder. Astronomers first build the ladder by selecting nearby Cepheids and measuring their distances against light. Wendy Friedman, an astrophysicist at the University of Chicago, explained that subsequent steps use only Cepheid variables. Next, cosmologists looked at the distances of the stars and supernovae on each bar and compared the extent of the redshift of their light, which shifts toward longer red wavelengths as the universe expands. This allowed for an accurate measurement of the Hubble constant. In 2019, Rees' team used this method to target the Hubble Space Telescope at one of the Milky Way's nearest neighbors, the Large Magellanic Cloud. Their results were strikingly high, showing an expansion rate of 74 kilometers per second per megaparsec, compared to Planck's measurement. However, Hubble lacked the accuracy required for the messy regions of space the team was studying, causing some of the distant Cepheids to blend with nearby stars. Critics have argued that this stunning result might have come from a measurement error. So when James Webb launched in December 2021, it was poised to either resolve this discrepancy or confirm it. At 6.5 meters wide, Webb's mirror is nearly 3 times larger than Hubble's, which is only 2.4 meters wide. Additionally, James Webb can detect objects nearly 10 times fainter than Hubble and is also far more sensitive in the infrared range, allowing it to observe across a broader spectrum of wavelengths. By comparing the Cepheid variables measured by James Webb and the galaxy NGC 4258 with bright type Ia supernovae, another kind of standard candle, since they all explode with the same absolute brightness, Rees and his colleagues produced an almost identical result, 73 kilometers per second per megaparsec. Other measurements, including one made by Friedman with the Hubble Space Telescope of the fast brightening of the red supergiant branch, and another of light bent by gravity from massive galaxies, returned values of 69.6 and 66.6 kilometers per second per megaparsec, respectively. Another result, using light bending, also gave a value of 73 kilometers per second per megaparsec. Cosmologists were baffled by these results. Rongzhen Kai, a cosmologist at the University of California, Merced, who worked on the Hubble constant translation, said, "The temperature of the CMB is measured to 1% accuracy, and the distance scale of the Cepheids is well understood. The cosmic microwave background, CMB, a relic of the universe, offers a pivotal clue to understanding its early dynamics and formation. Formed just 380,000 years post-Big Bang, this ancient light presents a snapshot of the universe at a critical stage of development, encapsulating the aftermath of the initial expansion. As the universe cooled, protons and electrons combined to form neutral hydrogen atoms, allowing photons to travel freely. These photons, now redshifted due to the expanding universe, create the CMB, a nearly uniform radiation field permeating the cosmos. By studying the subtle variations in the CMB, scientists can glean insights into the distribution of matter, energy, and the overall geometry of the universe. The CMB serves as a cosmic time capsule, offering a glimpse into the primordial processes that shaped the cosmos, and continues to be a cornerstone in our understanding of cosmology. From its role in confirming the Big Bang to providing the most accurate measurements of the universe's age, the CMB remains a critical tool in deciphering the universe's evolution. The current discrepancies in measuring the Hubble constant using the CMB and other methods underscore the need for continued exploration and refinement of our cosmological models. As new technologies and telescopes, like the James Webb Space Telescope, continue to push the boundaries of observation, the quest to resolve these discrepancies and uncover the true nature of the universe's expansion continues.